Сегодня, может быть, чуть-чуть подольше поболтаю, ничего?
Да, я вообще никуда не тороплюсь.
Ну, правда, сможешь часа половину выгнать.
Это да.
Но я не очень помню, у меня все есть в искусстве, у меня сегодня уже экзамен. Ладно, наверное, нужно уже начинать. В этот раз это сработает, как ни странно. Okay, so at the end of the previous lecture, I forgot to complete the proof of the theorem, and no one told me about that. So the theorem was about the injective tensor product. We wanted to prove that the completed injective tensor product preserves injections. That is, you have two injective continuous linear maps between complete locally convex spaces. Then the injective tensor product of these maps is also an injective map. And we observe that everything is actually reduced to the following proposition. You have complete locally convex spaces x, y, and z. Complete locally convex spaces. And an injective continuous linear map phi from x to y. Then, if we take the injective tensor product with the identity map of z, so the resulting map acts from z tensor x to z tensor y, then this map is also injective. And we discussed the following special case. Case 1, the case where Z is a Banach space. So this was considered at the previous lecture. And that's it. So this was the end of the lecture. And I forgot to consider the general case. So let's consider the general case now. The general case is reduced to the case where Z is a Banach space as follows. We represent Z as a reduced projective limit of Banach spaces. We know that every complete locally convex space can be represented in this way. And we look at our map. Z tensor x to Z tensor y. We already know that the complete injective tensor product commutes with projective limits, with reduced projective limits. So this is isomorphic to the projective limit of Zi tensor x, and this is isomorphic to the projective limit of Zi tensor y. And we have a natural map from here to here, which is also easily seen to be injective. Well, indeed, for each I we have an injective map from here to here, and we call that the projective limit is naturally embedded into the product. Projective limit is embedded into the product. Both for x and for y, and clearly the product of injective maps is injective. So this one is also injective, and this completes the proof for the general case. As an application of this result, let's discuss a useful exactness property of the complete tensor product, complete projective tensor product for nuclear Fréchet spaces. The exactness. the complete projective tensor product for nuclear Fisher spaces. We start with the following result, in which we consider only short exact sequences. Suppose we have a short exact sequence of Fisher spaces, phi and psi, an exact sequence of Fisher spaces. When I say exact, I mean exactness in the pure algebraic sense. That is, the theoretic range of every arrow is equal to the kernel of the next arrow. So it is an exact sequence of Fisher spaces, and Y is also a Fisher space. And suppose that either X2 or Y is nuclear. I claim that if we consider the tensor product of this sequence by Y, then the resulting sequence will be exact. This is a useful result, and it has many applications in neighboring fields of mathematics. To prove this proposition, let's observe, first of all, that the open mapping theorem implies that psi is open and phi is topologically injective. Well, indeed, phi is surjective, so it is open, and phi is an injective map with the closed range. The range of phi is equal to the kernel of psi, which is closed. So phi is an injective map with closed range, and so it is topologically injective, again by the open mapping theorem. So in particular, x1 is a subspace of x, is isomorphic to a subspace of x2, and x3 is isomorphic to a quotient. And know that subspaces of nuclear spaces and quotients of nuclear spaces are also nuclear. And as a result, we see that everywhere in the sequence, the projective tensor product is equal to the injective tensor product. Everywhere in this sequence that's denoted by star. Well, indeed, this is clear if Y is nuclear, because for nuclear spaces, the tensor product, the projective tensor product is equal to the injective tensor product. So this is clear if Y is nuclear, but if X2 is nuclear, we automatically have that X1 and X3 are also nuclear, and this implies the result. Okay, now we also know that psi tensor 1 is surjective. Psi tensor 1, and it is surjective because this is the general property of the projective tensor product. The projective tensor product of two surjections between Fisher spaces is surjective. And we also know that the range of phi tensor 1 is dense in the kernel of psi tensor 1. This is dense in the kernel. Again, this is a general property of projective tensor product. It preserves co-kernels, and explicitly this means that we have, in particular, this property. In particular, we see that the sequence is exact in here by the surjectivity of this map. But on the other hand, we know that phi tensor 1 So we can replace here the projective tensor product by the injective tensor product. And this map is topologically injective, because the completed injective tensor product preserves topological embeddings. And this already implies the exactness of our sequence in the remaining terms. The exactness at x1 tensor y and at x2 tensor y. Well, indeed, since this map is injective, we see that our sequence is exact here, but it is topologically injective, so its range is closed, but we already know that its range is dense in the kernel, so as a result, the range of this map is equal to the kernel, and we have exactness here. Now this completes the proof. Useful exercise is to prove that this result holds under the assumption that only x1 is nuclear. The result holds if we assume that only x1 is nuclear. And now can generalize our proposition as follows. Suppose we have an exact sequence of Fisher spaces of the following form, so we don't consider 0 here and 0 here. So in other words, phi is not necessarily injective, psi is not necessarily surjective. The exact sequence of Fisher spaces. Y is a Fisher space. And again, suppose that either x2 or y is nuclear. And I claim that in this case, the tensor sequence is again exact. So this is a generalization of this proposition. The idea is to reduce everything to the previous proposition as follows. So let K denote the kernel of psi, and let C denote the quotient of x2 modulo K. So we have an inclusion map I from K to x2, and the quotient map Q from x2 onto C. So we get a short exact sequence, 0, K, x2, and C, and we apply our proposition, and we get an exact sequence. So the following sequence is exact. K tensor y, x2 tensor y, and C tensor y. This is P tensor 1. This is, oh, sorry, I tensor 1. And this is Q tensor 1. But this is not what we want to prove. So how is this sequence related to our sequence? So this is x1 tensor y. This is x3 tensor y. And here we have phi tensor 1 and psi tensor 1. So we want to show that this sequence is exact. Well, we have a map from here to here. So since K is kernel of psi, we see that phi takes x1 to K, and we may consider we consider the tensor product of this map with Y. And we observe that this error is surjective because the map from x1 to K is surjective. Our initial sequence was exact. So this map is surjective. On the other hand, we have a map from here to here, which is induced by psi. So psi takes x2 to x3. When we quotient out the kernel, we get a map from C to x3, which is, by the way, injective. But after we tensor it by Y, in general, we cannot claim that this one is injective, because the projective tensor product in general doesn't preserve injections. But let's now see that it is indeed injective. Why is it injective? Well, we have canonical maps from here to the injective tensor product. Oh, so maybe I should somehow stress that this sequence is exact, and this is something which is outside the sequence. So this is the injective tensor product of C and Y, and here we have an isomorphism because, well, either Y or C is nuclear. Here we can also consider the injective tensor product of X3 and Y. In general, this is not necessarily an isomorphism, but because X3 is not necessarily nuclear, and Y is not necessarily nuclear. But anyway, this map is injective. This map is injective because the injective tensor product preserves injections. But this reason implies that this map is also injective. Because if it is not, then this composition is not injective. This one is not injective, but this composition is injective. So this is also injective, and now a simple diagram chasing shows that the sequence we want, this sequence, which is here, is also exact. This is a simple exercise in diagram chasing. Okay, so as a corollary, we see that the projective tensor product preserves kernels on the category of nuclear Fisher spaces. So if psi is if phi is kernel of psi and the conditions of our theorem are satisfied, then phi tensor 1 is the kernel of psi tensor 1. So we know that the projective tensor product preserves co-kernels, but on the category of nuclear Fisher spaces, it also preserves kernels. And to prove this result, we simply consider the following exact sequence. This is phi, this is psi, and we apply first our theorem to this segment of our sequence, and then we apply the same theorem to this part of our sequence. And we get that the tensor sequence is also exact. Okay. As an application of this result, let's now discuss tensor products of spaces of holomorphic functions. Suppose that M and N are complex manifolds. I claim that then there exists a topological isomorphism between the projective tensor product of spaces of holomorphic functions on these manifolds and the space of holomorphic functions on the product, which takes every elementary tensor, f tensor G, to the function given by the following formula. The proof is naturally divided into several steps. So case 1, if we know that this result is true if both M and N are polydisks. This is true if M and N are polydisks. This was discussed some time ago, and we deduced this as a corollary of the Grothendieck-Peach nuclearity criterion for Kyoto spaces, and not exactly of this, but just of the general result which describes the projective tensor product of Kyoto spaces. Okay, case 2. Suppose that now M is a polydisk and M is arbitrary. And let's take an open cover of M by polydisks. Open cover, and each UI is an open set by holomorphic equivalent to a polydisk. Then we have the following standard exact sequence of the following form. So O of M is mapped to the product of O of UI, and this is mapped to the product of over all pairs I and J of spaces of holomorphic functions on the intersections. So phi and psi. This is a standard exact sequence, which is defined as follows. Phi takes every holomorphic function to the family of its restrictions to the sets UI, and psi takes a family of holomorphic functions Fi to the family in this product indexed by pairs I and J. And this is just Fi restricted to the intersection minus Fj restricted to the Fj restricted to the intersection. So trivially the sequence is exact. So we can consider the tensor product of this sequence by sorry, this is not M, this is M. This is M. We have chosen cover of M by polydisks. So this is M. So we take the tensor product of the sequence by O of M, and we get the following. O of M tensor O of M. Now we use the fact that the projective tensor product, the complete projective tensor product, commutes with products. This was proved at the previous lecture. So we get this and this. On the other hand, if we consider the product of M and N, this manifold is covered by the products of M and UI, and we get a similar sequence for this specific cover of M tens cross UI. And here we have O of M cross UI intersected with M cross UJ. And we have an initial map from here to here, which appears in the statement of the proposition. Clearly, it is well defined by the universal property of the projective tensor product. And here we have isomorphisms. For the simple reason that both M and UI are polydisks. And for polydisks, we already know that this map is an isomorphism. And the rules are exact. And this really implies that this first horizontal arrow is an isomorphism. And actually, it is a topological isomorphism modulo the open mapping theory. It is an algebraic isomorphism for obvious reasons, but it is bijective and continuous, so it is a topological isomorphism. So this completes the proof in the case where M is a polydisk and M is arbitrary. And finally, we consider the more general case, case 3, M and M are arbitrary. Now take an open cover of M by polydisks. J. Each open set Bj is biomorphically equivalent to a polydisk. And we apply essentially the same argument. As in case 2. So now we can use the fact that our theorem is true if only one of the manifolds is a polydisk. We draw a similar picture and we deduce that our map is an isomorphism for arbitrary complex manifolds M and N. Okay, in fact, by using a similar argument, we can prove the respective result for spaces of smooth functions on smooth real manifolds. Suppose that M and N are smooth real manifolds. Then there exists a topological isomorphism between the projective tensor product of the spaces of smooth functions on M and N, and the space of smooth functions on their product, given by the same formula. So it takes every elementary tensor to the function, which takes each pair x and y to the product of f of x and g y. The proof is more or less the same, so this is an exercise for you. So everything actually reduces to the topological isomorphism between the projective tensor product of C infinity over Rm and C infinity on Rn to the C infinity of on Rm plus M. And we have already discussed this isomorphism some time ago. This was also an exercise, but this is much easier. So this can be reduced to. Actually, we discussed this isomorphism in the case where we have the injective tensor product here. But now we already know that the projective and the injective tensor products for nuclear spaces are the same. So we can use this. Okay. Now our next goal, and this will be the final goal of our course, is to discuss an application of topological vector spaces to complex analytic geometry. So what we want to do is to prove the Cartan-Serre finiteness theorem. Finiteness theorem. This theorem tells us something about the cohomology of coherent sheaves on compact complex manifolds. So I'm assuming you know something about sheaves and cohomology. But nevertheless, let's start by recording some basic facts about the Czech complex. The Czech complex. So suppose that X is a topological space, and suppose that F is a sheaf of abelian groups. On X. And suppose that we have an open cover of X, so the elements of the cover will be indexed by an arbitrary set I. Open cover of X. Let's introduce some notation. If alpha is an ordered n plus 1 tuple of elements from I, then we denote by U alpha the respective intersection of UI0, so on UI and we denote by Cn of UF the product over all alpha in over all n plus 1 tuples alpha of the section spaces of F over U alpha. And we call this product the group of Czech n cochains. These groups can be arranged into a cochain complex as follows. We define map Dn from Cn to Cn plus 1 as follows. Dn of F. So to define Dn of F, we must explain what are the components of this cochain. So we must explain what is Dn of F indexed by I0 up to In plus 1. And this is defined as the following alternating sum over k from 1 to, from 0 to n plus 1. Here we have a sign 1 minus 1 to the power k, and we take F and restrict F to, we take F, we consider the coordinates of F where ik is thrown away. So after we throw ik away, we get an n plus 1 tuple, so this is well defined, and we get the alternating sum restricted to the respective set u I0 In plus 1. A simple calculation shows that the composition of the neighboring maps is 0, so we get a cochain complex, and this complex is called the Czech complex, and is denoted by C of UF. This is the Czech complex. For F and U, for the sheaf F, and the cover, the open cover U. So let's now observe. Let's now look at the zeroth cohomology of this complex. So the zeroth cohomology is just the kernel of D0. So D0 acts from the product of sections over all elements of our cover, f of ui, and it consists exactly of those elements of this product which are contained by all the intersections. And just by the definition of a sheaf, this is nothing but the space of sections of over X. or in other words, this is the zeroth cohomology of F. In some cases, a similar result holds for the higher cohomology groups. So let's give the following definition. If U is an open subset of X, we say that F is cyclic on U if the higher cohomology of F vanishes over U. And we say that the open cover U is an acyclic cover or Leray cover for F. If F is a cyclic on all finite intersections, if F is cyclic on U alpha for every n plus 1 tuple alpha, and for every n. And we have the following result. Theorem 1, due to Leray. If U is an acyclic cover for F, then there exist isomorphisms between the nth cohomology of the Čech complex and the nth cohomology of our sheaf. And in fact, these isomorphisms are natural in F if we consider the class of those sheaves for which U is an acyclic cover. This result can be refined a little bit. And to refine this result, let's recall the following algebraic definition. Suppose we have two co-chain complexes, C and D, for example, of abelian groups, but in fact, the definition makes sense in any abelian category. You have two co-chain complexes, and if you have a morphism between C and D, the chain map, then we see that we say that phi is a quasi-isomorphism. And we abbreviate it like this. If it induces an isomorphism cohomology. So Hn of phi is an isomorphism for every n. Of course, if phi is an isomorphism, then it is a quasi-isomorphism, but clearly the converse is not true. For example, if C is exact, then it is quasi-isomorphic to 0. Okay, let's now come back to our situation, and suppose that we have two open covers, U and V, open covers of X. So U consists of open sets Ui, and V consists of open sets Vj. And we say that V is a refinement of U, in Russian измельчение. If every element of V is contained in an element of U. Every element of V is contained in some element of U. Equivalently, this means that we have there exists a map, a refinement map, phi from the index set J to the index set I, such that for every J, Vj is contained in U phi of J. And in this case, we can define the so-called refinement morphism between the respective Čech complexes. I star from the Čech complex of the bigger cover U to the Čech complex of V for the same sheaf F as follows. In degree n, this morphism takes an n cochain of F over U to an n cochain of V given by the following formula. So the respective component of F, of phi n of F, is just the, so we take the component of F corresponding to the indices phi of J0 up to phi of Jn. So by assumption, the set corresponding to these indices is bigger than the set corresponding to these indices. So we simply restrict this section to Vj0 up to Jn. And it's easy to see that phi star is a morphism of cochain complexes. Okay, now theorem 2, also due to Leray, says that if U and V are a cyclic covers for F, and V is a refinement of U, then the respective refinement map, phi star, is a quasi-isomorphism. Is a quasi-isomorphism. Okay, so that's all we want to know about Čech complexes. Now let's recall some definitions related to coherent analytic sheaves. So suppose now that X is a complex manifold. And we denote by O the structure sheaf of X, that is the sheaf of germs of holomorphic functions of X. By an analytic sheaf of X, we mean a sheaf of all molecules. A sheaf of modules over the sheaf of germs of holomorphic functions. And we now define a coherent sheaf as follows. If F is an analytic sheaf of X, we say that F is coherent if for every point X there is a neighborhood U of X, and an exact sequence of the following form. And there's an exact sequence of the following form for some non-negative integers m and n. Here are some examples of coherent sheaves. Of course, the structure sheaf is coherent for obvious reasons, as well as the free sheaf, O to the power n. Also, it's clear that any locally free sheaf, that is an analytic sheaf which is locally isomorphic to a free sheaf, is also coherent, because the coherence is clearly a local property. And in fact, there are many other natural examples. Actually, when I say that the structure sheaf is coherent, I'm cheating a little bit here, because in fact, there is an original definition of a coherent sheaf is slightly more general, and it makes sense for a sheaf of modules on any ringed space. So this definition is slightly more involved. But if we know that the structure sheaf is coherent in the sense of this more general definition, then it turns out that this more general definition of a coherent sheaf can be simplified like this. And there is a deep theorem due to Oka that the structure sheaf of a complex manifold is coherent in the sense of this more general definition, which I'm going to give you in this course. So as a result, since we are speaking only about analytic sheaves, that is, sheaves of modules over sheaves of gerbs of holomorphic functions, we can use this simplified definition of coherence. But in the general case, if we use the more general definition of a coherent sheaf, then the coherence of this structure sheaf is a deep theorem due to Oka. Okay, well, by the way, what is a locally free sheaf? A locally free sheaf is the same as the sheaf of sections of a holomorphic vector bundle. So we see that coherent sheaves generalize vector bundles. And in many cases, coherent sheaves are more convenient than vector bundles. For example, for the following reason, I have the following useful effect. You will have a short exact sequence of analytic sheaves, G and H, short exact sequence of analytic sheaves. Then G is coherent if and only if F and H are both coherent. And this is very useful for locally free sheaves. That is not true. But the quotient of a locally free sheaf is not necessarily locally free, but it will be coherent, and it's very useful. Now, what can we say about cohomology of coherent sheaves? It turns out that there is a very nice and important class of complex manifolds for which the higher cohomology of coherent sheaves is trivial. So let's give the respective definitions. Suppose that X is a complex manifold. Then K is a compact subset of X. We define the holomorphically convex hull of K as follows. This is a set K hat, which consists of those points X in our manifold X, such that for every holomorphic function f on x, the following inequality holds. The absolute value of f of x is less or equal to the supremum of f or k. For example, if x is the complex plane and k is the circle, then the maximum modulus principle implies that the holomorphically convex hull of the circle is the closed disk. We now give the following definition. We say that our complex manifold X is a Stein manifold. If it satisfies the following two conditions. Condition one is that the space of holomorphic functions on X separates the points. Separates the points of X. In some sense, we have many holomorphic functions defined everywhere on X. And condition two is more technical, but is also important. It states that for every compact set K in X, its holomorphically convex hull is also compact. And here are some examples. Cn is a Stein manifold. And more generally, any convex open set, convex open subset of Cn is also a Stein manifold. This is not very hard. What is a little bit harder is to show that any open set on the complex plane, any open set on the complex plane is actually a Stein manifold. But there are also non-examples. If X is a compact manifold, compact manifold X of dimension, of positive dimension, is not a Stein manifold because by the Liouville theorem, if it is connected, then all homomorphic functions are constant. And if it is not connected, then the space of then all homomorphic functions are locally constant. So definitely they don't separate the points. And another non-example is looks as follows. We can take Cn and throw away a point, a single point, 0. It turns out that this is not a Stein manifold. Clearly, homomorphic functions separate the points in this case, so condition 1 is satisfied, but condition 2 fails. So this is not a Stein manifold. For Stein manifold, we have the following important results. The following important result, the so-called theorem B. There is also theorem A, but we don't need it today. The theorem is due to Henri Cartan. If I'm not mistaken, 1951. And this theorem tells us that if X is a Stein manifold, then every coherent analytic sheaf of X is a cyclic of X. This is very useful. This is very useful, but we will not prove this result today. It's highly non-trivial. What we are going to prove is a result about the homology of coherent sheaves on compact complex manifolds. This theorem is due for fun and zero. Zero. 1953. Suppose that X is a compact complex manifold. So, in some sense, it is an opposite case. So, compact complex manifolds are never Stein. And F is a coherent analytic sheaf. On X. The theorem states that the cohomology spaces of F over X are finite dimensional. For every I, 0, 1, and so on. In particular, this is true if I equals 0, so the section spaces are finite dimensional. Now, this is a generalization. In some sense, this is a generalization of the Liouville theory. So this is our goal. And before we can prove this, so we need some preliminaries. So part 3. First of all, we want to topologize the section spaces of coherent analytic sheaves. Topologizing the section spaces. Of coherent analytic sheaves. So suppose that X is a complex manifold, and F is a coherent analytic sheaf on X. First of all, we take a small open set which appears in the definition of a coherent sheaf. So suppose U is an open set, and suppose there exists an exact sequence of the following form. Over U. So K is, this arrow appears in the definition of a coherent sheaf, and K is just the kernel of this arrow. And K is finitely generated by finite generated sheaf, which appears which is just the kernel of this one. Okay, so we know now that this exact sequence induces a long exact sequence of cohomology spaces, but we know that K is coherent. So H1, the first cohomology group. I must also assume that U is a Stein open set. Stein open set. We can always assume that U is Stein because, a polydisk is a Stein manifold, and every open subset of X can be covered by open sets by holomorphically equivalent to a polydisk. So, without also generality, we may assume that U is a Stein open set. So, since it is a Stein set, we see that the first cohomology of K vanishes. This is 0. And so this, as a result, the sequence of section spaces is exact. In particular, we see that we have a surjective map from O of U to the power n to F of U. This is onto. So we may equip F of U with the quotient topology. u with the quotient topology. O of u is already topologized. This is the space of homomorphic functions. It carries the canonical compact open topology. This is the nth power. It is also topologized, and we equip f of u with the quotient topology. We have the following fact, which is not entirely trivial, but it's true, that this topology is Hausdorff. This topology is Hausdorff. And also, this is much easier, so this is an exercise for you. This topology doesn't depend on the choice of this exact sequence. This topology doesn't depend on the choice of our short exact sequence. This is a nice application of the open network theory. Okay, so as a result, we see that f of u is already topologized if u is small enough. And now take an arbitrary open set. An arbitrary open set. And let's take an open cover. Let's put it to u. Open cover of u such that f of ui, the section spaces over ui, are already topologized. And we equip f of u with the projective topology generated by the family of restriction maps. We have restriction maps from f of u to f of ui over oi. And again, so it becomes a locally convex space. And again, we have the following exercise. This topology doesn't depend on the choice of our open cover. And again, this is an application of the open mapping theorem. And the resulting space f of u becomes a nuclear Fisher space. A nuclear Fisher space. Why is it nuclear? Well, the second part is very easy. It is nuclear because if u is small enough, then it's a quotient of a nuclear space, O of u to the power n. So this is nuclear, and the quotient of a nuclear space is nuclear. And we also know that the class of nuclear spaces is stable under taking projective locally convex topologies. So f of u is nuclear. Why is it metrizable? Again, if u is small enough, it is metrizable because it is the quotient of O of u to the power n. So this one is metrizable, and so this one is also a Fisher space. And in the general case, we can consider only countable open covers. Without loss of generality, we may assume that this open cover is countable. And so this implies that f of u is also metrizable. So it is a nuclear Fisher space. Okay. Our next step, and this is the main analytic step of the proof, is the Schwarz-type theorem on nuclear perturbations. And here's the theorem. that X and Y are Fisher spaces. F and U are continuous linear maps from X to Y. We also assume that F is onto and U is nuclear. U is nuclear. I claim that in this case, the co-kernel of F minus U is finite dimensional. So this is the main analytic part of the proof of the Cartan-Serre theorem. In fact, the proof of the Cartan-Serre theorem, which we discuss here, is different from the original proof due to Cartan and Serre. In fact, the original proof was based on the Schwarz theorem, which is not about nuclear perturbations, but is about compact perturbations. But the original form of the Schwarz theorem is much more involved, and it turns out that in the case of nuclear perturbations, the proof can be essentially simplified. So actually, this is based on a later paper by Reinhard Kiel and Jean-Louis Verdier, where a much more general result is proved. So they prove the so-called Grauert direct image theorem, which states that the direct image of a coherent sheaf under a proper map is coherent. So in the special case where our map takes X to a point, what we get is precisely the Cartan-Serre theorem. So our approach to the Cartan-Serre theorem is actually a specialization of the proof given by Kiel and Verdier. Okay, so the proof of the Schwarz type theorem will be divided into several lemmas. Lemma 1. Suppose that X is a Fisher space, and U is a nuclear operator from X to itself. And I claim that the co-kernel of 1 minus U, where 1 is the identity map on X, is finite dimensional. Oh, by the way, I forgot to explain what I mean by co-kernel here. I mean, by co-kernel, I mean the co-kernel in the category of all locally comic spaces, not necessarily Hausdorff. So theoretically, this is just the quotient modulo of the range, equipped with the quotient topology. So the proof of lemma 1. First of all, we observe that the result is true if X is a bar space. This is true if X is a bar space. And this readily follows from the classical Ries theorem. Which is normally proved in any standard functional analysis course. So 1 minus U, if U is a compact operator on a bounded space, then 1 minus U is a Fredholm operator of index 0. In particular, its co-kernel is finite dimensional. So let's now consider the general case. And let's decompose, let's factorize U through a bounded space. So every nuclear operator factorizes through a bounded space. This is U1, U2. E is a bounded space. And when we see that either U1 or U2 is nuclear, let's assume that U1 is nuclear. U1 is nuclear. And let's consider the full operator V on E, which is U1, U2. This is a nuclear operator on E. And let's consider the following picture.
this is 1 minus u. It acts on x, and we put here the co-kernel of this map, 1 minus u. Here we have 1 minus v, which acts on e, 1 minus v. And we have a natural map to the co-kernel of this map here, co-kernel of 1 minus v. And again, we repeat the first row, y minus u, x, and the co-kernel, 1 minus u. So here we have u1 and u2, u1, u2, u1, u2. And it's immediate to check the diagram commutes. So this is, for example, the composition of these two arrows is u1 minus u1. Is that correct? Yeah. u1, u2, u1. Yeah. So u is u2, u1. So this composition is u1 minus u1, u2, u1. And this composition is u1 minus u1, u2, u1. Okay, that's true. So the diagram commutes, and as a result we have induced maps here, which will be denoted by u1 bar and u2 bar. So this composition is u, this composition is u, and now it's easy to see that the composition of these maps, u bar, is just the identity map. Exactly because we quotient out the range of 1 minus u. After we quotient out the range of 1 minus u, the respective quotient map is the identity map. So we see that u2 bar composed with u1 bar is the identity map. In particular, u1 bar is injective. But we already know that this space is finite dimensional, and so this one is also finite dimensional. And this completes the proof of lemma 1. Lemma 2. Suppose we have a surjective continuous linear map between Frisch spaces. So x and y are Frisch spaces. And F is a surjective continuous linear map of x onto y. So y becomes a quotient of x.
Сейчас, почему у нас с чертой это единица?
Well, if we forget about the middle row and consider only the upper row and the bottom row, and forget for a moment about this arrow, then there is a unique map. Oops. Oh, okay. So if we forget about this row, then there is a unique map from here to here, which makes the diagram commute. And this is the identity map. Because we quotient out the range of 1 minus u. So how this arrow acts, it takes any element in here, takes a representative in here, implies u, and then takes a representative in here. Okay? And this will be the same element. The difference between this element and the element which is in here sits in the subspace which is quotient out. So this is the same element. U bar, and this is 1. Okay. So on the other hand, this is the identity map, but on the other hand, we can now look at this arrow and we see that the whole diagram commutes. So the composition of U1 and bar and U2 bar is the identity map. Okay, so now suppose we have a surjective linear map between Frisch spaces x and y, and a sequence yn, a sequence in y, which converges to 0. I claim that there exists a sequence sequence xn x, which converges to 0, such that xn converges to 0, and such that f of xn equals 1. In other words, we can lift sequences converging to 0. You have a surjective linear map between Fisher spaces, then every sequence in Y converging to 0 can be lifted to a sequence in X converging to 0. The proof is an exercise for you. Actually, we have already proved this result implicitly when we proved that the quotient of a Fisher space is a Fisher space. If you look at the proof of the completeness of the quotient, you will easily understand how to lift sequences converging to 0. So see the proof of the completeness of quotients of Fisher spaces. Okay, lemma 3. Lemma 3. Let's now imagine the following situation. So let's draw a picture. X, Y, and Z. So suppose we have Fisher spaces X, Y, and Z. Fisher spaces. A subjective continuous linear map F from X to Y. And the nuclear map U from Z to 1. I claim that U can be lifted to a nuclear map from Z to X. Then there exists a nuclear map V from Z to X such that the diagram commutes. Something like an algebraic projectivity condition, but not exactly, because we don't lift arbitrary maps, we lift only nuclear maps. So this is V. Okay, so U is nuclear, so we can write U as the sum of the following series: lambda n, fn, yn, the sum of series of rank 1 operators, where fn is an equicontinuous sequence of linear functionals on Z, and equicontinuous sequence in Z prime. Lambda m is absolutely convergent series of numbers. And Yn, if we look at one of the equivalent definitions of a nuclear operator, Yn is contained in a Banach disk, in some Banach disk in Y. But by changing Yn slightly, we may also assume that Yn converges to 0 in Y. Actually, they are contained in Banach disk. So we multiply Yn by a sequence of numbers which slowly converges to 0. It converges to 0 so slowly that this property still holds after we divide lambda n by the respective numbers. Anyway, so this is a simple exercise that we can arrange Yn. We can always arrange Yn in such a way that they converge to 0. And now we use lemma 2. We lift our sequence Yn to X. Lemma 2, there is a sequence Xn in X which converges to 0 and such that f of Xn equals Yn. And we now define V from Z to X as follows. V will be the sum of the following series. And this is more or less what we're looking for. The only thing to prove is that V is nuclear. So we want to show Fn is still like a continuous, so everything is okay with Fn, and lambda n is still absolutely summable, but we want to show that Xn, the sequence Xn, is contained in a Banach disk. But we can now explicitly define our Banach disk as follows. So that B be the absolutely convex whole of the set of all elements of our sequence. The closure of the absolutely convex whole. So it is a closed bounded because Xn converges to 0, a closed bounded absolutely convex set in X, and X is complete, so B is also complete. B is bounded, absolutely convex, and complete. So it is a bounded disk. And Xn is obviously contained in B, so we conclude that V is nuclear. V is nuclear. And this completes the proof. Okay, and now we can prove the Schwarz-type theorem. So let's recall a statement. So we want to show that if F is surjective of X onto Y, and Y is nuclear, then the co-kernel of F minus Y is finite dimensional. So we start with the following picture, which comes from lemma 3. So this is our U from X to Y. This is F from X to Y. U is nuclear, so we may lift U to a nuclear map from X to itself. Number 3, there is a nuclear V such that the diagram commutes. And now look at the following diagram. This is X, this is 1 minus V, this is X, and this is the co-kernel of 1 minus V. We already know that this one is finite dimensional. We can also consider F minus U, and the co-kernel of F minus U. If we want to show that this one is finite dimensional, but we can complete this picture to the commutative diagram as follows. We have the identity map here, and we have F here, and the diagram commutes. So this composition is F minus Fv, that is F minus U. So the diagram commutes, and as a result, we get a map from here to here, which is surjective because F is surjective. But this one is finite dimensional, and this implies that this one is also finite dimensional. And this completes the proof of our Schwarz type theorem. Okay. The last step, step number 5, in our proof of the Cartan-Serre theorem, will be about binuclear quasi-isomorphisms. And the proof of the Cartan-Serre theorem. First of all, we want to introduce a new class of maps the so-called binuclear operators. Suppose that X and Y are locally convex spaces, and phi is a continuous linear map from X to Y. We say that phi is binuclear if it can be decomposed as a composition of two nuclear operators. If phi equals phi2 composed with phi1, where phi1 is a nuclear operator from X to some locally convex space Z, and phi2 is a nuclear operator from Z to Y. And here's an important example, which will be needed in our proof of the Cartan-Serre theorem. Suppose that X is a complex manifold. F is a coherent analytic sheaf on X. U is an open subset of X. U and V are open subsets of X, such that the quarter of V is compact and is contained in U. Actually, this is an example and an exercise at the same time. So I claim, and this is an exercise for you, that the restriction map from f of U to f of V is binuclear. A hint to this exercise. First of all, it suffices to show that it is nuclear, because if we prove the nuclearity of this map, then we just find set W, which is somewhere in the middle between U and double V and U, and so this one is nuclear, and the composition is nuclear. So it's enough to prove the nuclearity of this map. And to prove the nuclearity, it's enough to factorize this map through a bound space. So a hint is to prove that this map factorizes through a bound space. This really implies that it is nuclear because any map from f of U to a bound space is nuclear. F of U is a nuclear space. Okay. So why do we need binuclear maps? This is the main advantage of binuclear maps as compared to nuclear maps. Suppose that X and Y are locally convex spaces, and phi is a binuclear linear map from X to Y, such that its range is contained in some closed vector subspace. Y1 is a closed vector subspace, such that the range of phi is contained in Y1. I claim that, so we can now consider phi as a map from X to Y1, and I claim that this resulting map will be nuclear. So formally this can be written as follows. So we consider a map phi 0 from X to Y1. So we define it by the same formula as phi. And I claim that phi 0 is nuclear. There is an exercise in our last exercise sheet which shows that for nuclear maps this is not true. If phi is nuclear and its range is contained in Y1, then phi 0 is not necessarily nuclear. But for binuclear maps, this is not possible. The proof is based on a trick which was already used when we discussed stability of the class of nuclear spaces. Ой. Уходим, да? Да, я помню, что вы говорили. Okay, so we have to move to another room. I apologize to everyone who looks this lecture via live stream, but we have to move to another room because there's another lecture there will be another.